Welcome to derivatives of a power. This is going to be the quotient rule and an applied problem. Right, so here's example one. And as soon as we see y equals something divided by something, we should be thinking quotient rule. So I've got the quotient rule here to remind us that it is the derivative. The derivative of a quotient is solved by taking the derivative of the numerator, the top part, multiplied the denominator, the bottom part, then subtracting the derivative of the denominator multiplied by the numerator, and finally dividing everything by the denominator squared. So you can see I've kind of color-coded some of those important parts there. And in step one, part one, or number one, you can see there's the actual calculus where the green is the derivative of the numerator. The blue is the physical denominator, and then we're subtracting the derivative of the denominator, which is the yellow, multiplied by the numerator, which is the orange, and then everything is divided by the denominator squared. And now you can follow all the rest of the steps, our algebra. If you need to pause the video and work through the algebra, do that now. All right, so here's example two. Same thing, I've got things color-coded so you can see the calculus in the first step. Go ahead and pause the screen and work through that problem also. All right, so here's a pretty cool applied problem. So how are we going to use this math? So in example three, we're asking to find the velocity of an object after 3 seconds of travel, where the distance s is in meters as traveled by the object is given by the s equals t plus 1 divided by the square root of t squared minus 1. So the s is the function, and we can convert that to y and x and then graph that in Desmos. And I've got that here. So what we're going to do is take the derivative of the function and then do like the f prime type example, where now we can find the actual instantaneous rate of change after 3 seconds. So you can see here in part 7 or number 7, we've got the derivative of the function. In the next slide, we're going to show you how to deal with that. So now that we've got the derivative of the function ds dt, we want to find the f prime, or in this case it would be s prime, at 3 seconds. But that's going to be equal to the rate of change, which is going to be the velocity of the object at 3 seconds. So you can see now we've put the 3 in and we're solving for the s prime 3 seconds, and we get an s prime at 3 seconds equal to minus 173.777 times 10 to the minus 3, and these would be meters per second. So how do we know? This kind of makes sense maybe at this point. We're using calculus to solve a problem, but how do we verify that it is actually we're solving this problem? So one way to double check our work, if you would, and make sure that we've either done the calculus and the algebra 100% correctly, or even to verify that this type of math even works. So one way to do it is to zoom way in. I've got the curve of the function here in Desmos on the top image. The bottom image is Desmos, same function, but zoomed way in on that line. So we can see and at point 3 is kind of in between these two dots that have been plotted, or 3, sorry. So we want to find what is the slope, or what is the rate of change at 3 if we were going to do it basically like old school method, non-calculus method. And we'd solve for m is equal to delta y over delta x. And I've just plotted a couple points here on the line that are like roughly centered or around the number 3. So that we should, once we get the slope of that, we should be able to kind of say, well, that should be close to what the instantaneous slope is at 3. And you can see the math here. You end up with 1.4 times 10 to minus 3 over negative 8 times 10 to the minus 3. And that gives us a roughly measured slope of negative 175 times 10 to the minus 3 at 3. And so that checks out. That looks really good. That's very, very, very close to our calculated rate of change using calculus.